In this video, we are talking about measuring deviation from ideal gas behavior. So there are two conditions. First is going to be the effect of pressure. Now here we've plotted a graph between PV by nRT and P itself. So PV by nRT is equal to Z, and this is basically, this Z is called as the compressibility factor. Now, this has been derived from the equation PV equals to nRT. We're just assuming that Z is a particular value. For ideal gases, since PV equals to nRT, Z will be equal to 1. Okay, and based on the value of Z, you have two different kinds of curves that you observe. The first one is when you have a positive deviation. So positive deviation is when Z is more than 1. So here, if you notice, these values where Z, the value of Z is more than 1, all of these show a positive deviation. On the other hand, these values down over here, these show a negative deviation. So the main difference between the positive and negative deviation is that in this case, that is in case of a negative positive deviation, the gas is going to be less compressible than expected. So in this area, all these gases, especially, above 1. So it includes this particular area. These gases are going to be less compressible than that of an ideal gas, or that which we expect. On the other hand, over here, if you notice, all of these cases, the value of Z is less than 1, which means it is showing a negative deviation and a gas is more compressible than expected. That's all you need to know for now. Okay, so what are we taking? We're taking a graph between the values Z, which is PV by nRT, versus pressure. And we're noticing that there are two kinds of curves that we observe. First, let's just talk about this. Z is equal to 1 is going to be for real gas. In that case, PV equal to, okay, I tried writing PV equal to nRT, but yeah. So PV is equal to nRT because Z equals to 1. On the other hand, here you have two types of values for Z. The first case, you're having Z is more than 1, and that includes all of the values of Z above this ideal gas line. And in this case, gases are less compressible than what we expect them in terms of, or what we expect from them. On the other hand, when this value of Z is lesser than 1, here we have a negative deviation. And in this case, the gases are more compressible than what we expect them to be. Okay, so right. So here for ideal gases, that is going to be equal to 1 under all conditions of pressures and temperatures. And because of that, we get the equation, the ideal gas equation, that's PV equals to nRT. Now, over here, I told you that there are two cases where, you have a value Z is greater than 1, Z is lesser than 1. Let's look at the individual gases. Now, in case of hydrogen, okay, as the value of pressure is increasing, there is an increase in the value of Z. So there is an increase, constant increase, which means in all the case for hydrogen, okay, no matter what the value of pressure, the Z value is always greater than 1. So here it is showing a positive deviation. And because it's showing a positive deviation, hydrogen is going to be less compressible than expected. Okay, on the other hand, when we talk about gases like carbon dioxide, methane, or oxygen, notice first you have a value lesser than 1 for Z. Okay, here if you notice this area, I should have probably included this curve as well, but it includes this curve. So in this area, the value of Z is less than 1. Okay, and this is at lower pressures. So at lower pressures, the value of Z is lesser than 1. So and this means that these gases are going to be more compressible than expected over here. And as the value of Z is increasing, because there is an increase in the value of pressure, they are going to be less compressible. Okay, so at low pressures, the gases are more compressible, and at high pressures, they are less compressible. So first of all, I'm assuming you understood whatever we discussed in the previous slide, where the value of Z decides if a gas is going to be less or more compressible. Just to recap, if the value of Z is greater than 1, the gas is more compressible. On the other hand, sorry, gas is less compressible. I'm really sorry. If Z equals is greater than 1, the gas is less compressible. Okay. And when Z is less than 1, the gas is more compressible. So for gases like hydrogen, because the value of Z is always greater than 1, they are always going to be less compressible than expected. On the other hand, for gases like carbon dioxide, methane, and oxygen, if you notice, there's a minima value that we get. Okay, and this minima is basically showing, this area is just showing us that at these conditions of pressures, these gases are going to be, first, they're going to be first they're going to be more compressible, and then as they cross this ideal gas, this one where Z equal is greater than 1, they will become less compressible. So in conclusion, for gases like nitrogen, oxygen, methane, carbon dioxide, etc., Z is less than 1 at low pressures, and this means that they are going to be more compressible at low pressures, and at a higher pressure Z is greater than 1, and in that way, and because they are it's greater than 1, it's going to be less compressible. So this, then ideal gas behavior, we are comparing it to ideal gas behavior. So that is about pressure. Okay, pressure, we are comparing it with the compressibility factor Z, and P, that is pressure in bar. Next is going to be obviously temperature. Now, if you notice over here, this is a graph which was observed for nitrogen, and here we are plotting PVM versus volume. Okay, VM is considered to be molar volume, that is V by N. Okay, and here these dotted lines show the ideal gas behavior that is expected. But as you go upwards, and these plots are drawn for individual temperatures. Okay, so as we go upwards, we notice that it's actually approaching the ideal gas behavior. And that is because at a higher temperature, gases tend to move towards the ideal gas behavior. Now, here, if you notice, the minimum curve is actually after this, there will come a temperature where this particular curve is going to vanish, and you're going to get sort of a same line in the beginning. And so this particular condition where the gases are behaving like an ideal gas, okay, that particular temperature is called a Boyle's temperature. And Boyle's temperature is going to be the temperature where it's going to be at an appreciable range of pressures as well. So let's assume T4, okay, is the Boyle's temperature for a particular gas. Okay, now T4 is considered to be the Boyle's temperature if it follows the ideal, if it shows the ideal behavior over a range of pressures. So various different types of pressures also it is able to show the ideal behavior. Then T4 is considered to be the Boyle's temperature. So based on the nature of the gas, that's going to decide the Boyle's temperature. Okay, and you have two conditions above Boyle's point, and in this case, you will have Z is greater than 1. So the forces of attraction is very small. And so if you remember, when Z is greater than 1, it is less compressible. Obviously, if you remember when we talked about the values of Z in relation to the compressibility, when Z was greater than 1, we said that the value, this meant that the gas is less compressible. And this is in turn because of the forces of attraction being very small. On the other hand, when you have a temperature below Boyle's point, the real gases, they show a decrease in the value of Z with increase in pressure. They reach a minimum value, and there's going to be an increase where you have a value of Z is increasing. And this is what we saw in the previous, in the previous graph. Now, all of this is taken into consideration, and the we are going to, excuse me, we are understanding the significance of Z. So for a real gas, Z equals to PV, volume of the real gas, by nRT. Now, if the gas is going to show the ideal behavior, you do not have to worry about the value Z because that's equal to 1. So V ideal becomes equal to nRT by P, and we are basically just substituting the nRT and P in this equation, and we get Z equals to V real by V ideal. So the value of the compressibility factor is basically the ratio of the actual molar volume of the gas to the molar volume of it if it were an ideal gas at that particular temperature and pressure. So we're comparing the actual volume, that is V real, versus the ideal volume if it was an ideal gas. Okay. So, but till now, we've not asked this one very essential question. Why? Why do these gases not show, I mean, these real gases show an ideal behavior at low pressures and high temperatures? Not only that, when you have a low temperature and a very high pressure, the gases seem to be deviating from the ideal behavior. And that was the question that was on the mind. Not only that, the two others over here, why do gases deviate from the ideal behavior, and what are the conditions under which gases differ from ideality? Now, there are two very important assumptions which were made by the kinetic molecular theory of gases that were wrong, or were a little, yeah. So what happened was, there are two postulates. These are two postulates which we studied. There is no force of attraction between the molecules of a gas. Now, assume there is no force of attraction between the molecules of the gas, you will not have the process of condensation taking place at all. Okay, condensation is happening because the molecules of gases are coming closer and closer to each other, and that in turn is going to lead to the conversion of the gaseous state to a liquid state. On the other hand, here there is another point that was put as a postulate. Volume of the molecules of a gas is negligibly small in comparison to the space occupied by the gas. And that was, I think, postulate number 2, if I am not wrong. But basically, in that postulate, we compared the empty spaces of the gas compared to that of the volume occupied by it. Now, if this was true, if this particular statement was true, if you remember when we talked about the volume and the pressure versus volume graph, which we noticed for the Boyle's law, we should have had the ideal and the real gas coinciding. But that's not the case. That's not something we observe. So these two assumptions uh, were not basically explaining certain properties of gas that was already observed. So because of that, that's why we have a real gas and an ideal gas, and an ideal gas is following the rules of the gas laws under all conditions of temperatures and pressures, whereas real gas do not. So with that, we're done with measurement of deviation. So first of all, we're talking about the effect of pressure. Here we have two kinds of deviations, which are, first we are plotting the graph between Z and P, where Z is the compressibility factor and it is equal to PV by nRT. For an ideal gas, Z equals to 1. That's how you get a straight line. So you have two kinds of deviations that we observe. First of all, Z is greater than 1. It's a positive deviation. In this case, the gas is going to be less compressible than we expect it to be. On the other hand, the negative deviation is when Z is lesser than 1. And in this case, gas is going to be more compressible than expected. So as we know, for ideal gases, Z equals to 1 under all conditions of temperatures and pressures. But this comes up only for real gases. So based on the gas, you have the values of Z less or greater than 1. So for gases like hydrogen, Z is always greater than 1, which means it is showing a positive deviation. And so this gas is going to be less compressible than expected. On the other hand, for gases like methane and carbon dioxide, first the value of Z is less than 1, and then it is greater than 1. And especially at lower pressures, the value of Z is less than 1, which means at this condition, these gases are going to be more compressible than expected. However, as the pressure is increasing, the value of Z is also increasing, and that's going to be more than 1. And that's why you have a the gas being less compressible than expected. Now, when we talked about temperature, this is a graph between for nitrogen between ppm and V. Here, as the temperature is increasing, the gas itself is these curves are approaching the dotted line. So there'll come a condition where this is almost coinciding. The minima will coincide with the dotted line, and that's when it's going to behave like an ideal gas. And this particular temperature where the gas is behaving like an ideal gas over a range of temperature, over a range of pressures is called as the Boyle's temperature. So above Boyle's point, we'll have the value of Z as greater than 1, and the forces of attractions are going to be very small, and so they are less compressible. On the other hand, below the Boyle's point, they will show a decrease in Z value with decreasing in pressure, and then they will reach a minimum value, and there'll be an increase in the value of Z. And here the value, and so first initially they'll be more compressible, and then they'll be less compressible than expected. So putting all of this together, we have something called as significance of Z. So Z for a real gas, Z is going to be equal to PV real, volume of the real gas, by nRT. And if the ideal, so basically we say V real is because pressure and the temperature is going to affect the volume. So if the gas is going to show ideal behavior, PV equals to nRT, so V ideal will be equal to nRT by P, and this whole part of this equation is getting replaced, and we get Z equals to V real by V ideal. And we conclude that the compressibility factor is actually the ratio of the actual molar volume of the gas, that is V real, to the molar volume of the gas if it acted as an ideal gas. Now, so in conclusion, we have the gases showing an ideal behavior at low pressures and fairly high temperatures, and in low temperatures and high pressures, it deviated from the ideal behavior. Now, there were two questions that came up: why do gases deviate from the ideal behavior, and what are the conditions under which they basically are deviating from the ideal behavior? So first of all, two assumptions which were made were wrong. No force of attraction meant that if a gas was compressed and it wouldn't have gotten converted to a liquid state if it did not have any forces of attraction between the molecules. On the other hand, if volume of the gas is negligibly small in compared to the space, if this particular theory was true, then the Boyle's the graph which we get for the Boyle's law, the real and the ideal gas should have coincided, and that's not observed. And so it is assumed that these two assumptions which were made were slightly mistaken. So with that, we're done with the measuring. In the next video, we'll be talking about how do we make sure that or rather what is done to the ideal gas equation to make sure it is followed for a real gas as well.